On the Virginia coast, hours away from any major airport, you'll find what appears to be a sleepy little town. It's not a tourist town or a beach town, that's all further down the road. Driving through, you'll see an abandoned roller rink and billboards for opioid abuse programs, a retro country radio station, and the seafood restaurant in the next town over. A single diner is nestled in a gas station right across the street from a house with half a dozen American flags and a huge Support Our Troops sign in the front yard. But when you drive a little further, you might start to wonder if there's more to this town than meets the eye. Down the road from the diner is the smallest Lockheed Martin building I've ever seen. Drive a minute longer and the forest clears. Immediately, you know there's more to this town. Your eyes are first drawn to giant satellite communication antennas and then to radar installations and what look to be huge airplane hangars emblazoned with the NASA logo. Of course, all of this is surrounded by fences with stern warnings for trespassers and loiterers, keeping gawkers at bay, leaving them to wonder what's going on in there. But thanks to you who follow us on YouTube and the EEs Talk Tech podcast, I wasn't left to wonder, and now neither are you. I'm Daniel Bogdanoff, and NASA granted me and select others special access to tour the Wallops flight facility. So, what is this place? As it turns out, it's a lot of things. The most exciting role of this place, for me anyways, is that it's the site of the Antares rocket launches. Twice per year, this sleepy backwoods town wakes up with a start. The world's top engineers, scientists, and researchers flock to the town. Wide-eyed high school students working the counter at the lone diner try desperately to feed a line of people that stretches way out the door. The hotels in the area are all completely booked. Because this weekend, we're going to space.
And Antares lifting on, going across the night sky, disappearing through some clouds quickly and coming quickly back into view. The first stage looking nominal or normal so far. Lighting up the night sky there above Virginia. Orbital ETK's Antares on its way.
Have you ever wondered what makes a place like this tick? There's an entire economy and ecosystem dedicated to keeping it afloat. I always thought that the rocketry aspect was the main attraction, and it certainly plays well on the media and on the internet, but I never gave much thought to the actual point of it all. Space is pretty cool, but what does humanity actually gain by getting there? And that's what we're going to look at today. We're going to explore the science, go past those warning-ridden fences, take a look at some of the projects that get a lot of press and some that are less glamorous. Then we're going to look at how those projects get deployed, and yes, that does include a rocket launch. Here we go. Day 1. It's Friday, May 18th. For me, it means travel day. One of the reasons Wallops Flight Facility is a great location is because that there's, quote, virtually unimpeded airspace. If you want to visit, this means that you have to drive from your major airport of choice for at least a couple hours, so it's going to be a long day. I figure I'll leave home around 7 a.m. and arrive at my hotel roughly 16 hours later. It's a long day for domestic travel, but what's a guy to do? As the plane doors close at the gate in Denver, I find out that the launch has been delayed 24 hours for additional spacecraft inspection. It's too late to get off the plane, so I shrug, text my wife I'm going to be another day on the road, and mentally score 1 point for fate. Fate 1, Daniel 0. From what I hear though, delayed launches are just part of the process. A delayed launch is better than a failed launch. When I land in DC, it's raining pretty hard, and I decide I don't really want to cram in a few hours of driving in the rain, so I scramble to rearrange lodging and catch a movie before bed. Take that, fate. Day 2, Saturday. I drive from DC to the coast and start to wonder if I'm really in the right place. I check my phone map and it says I'm on track. Once the woods clear and I see the comm arrays and the hangars with the NASA logo, I know I'm definitely in the right place. So, after showing a couple forms of ID to an armed federal agent,
none shall pass.
I get my pass.
All right, we'll call it a draw.
And I'm ushered into the day's event, the What's on Board mission briefing. This is when I start to think about more than just the rocketry.
It's super exciting to see a rocket launch.
This is Dr. Liz Warren, the head of the Center for the Advancement of Science in Space, which is a nonprofit NGO that manages all of the non-NASA research.
I want to remind you guys that when that launch goes and you're saying, go Antares, go Cygnus, say go science too. You're going to hear from scientists today who have spent a lot of time, a lot of energy, blood, sweat, and tears getting their payloads ready for the spacecraft and to go to space.
Scientists from around the country show off their experiments, which have been loaded into the Cygnus spacecraft, which then got stacked on top of an Antares rocket and is about to be delivered to the ISS, the International Space Station. They're being delivered on the OA9 cargo mission, which is why I'm in town. The OA9 mission is completely run by Orbital ATK. Orbital ATK is one of the 2 commercial companies with NASA launch contracts. The other is SpaceX, but don't compare them to SpaceX, it's a bit of a touchy subject around here. So this What's on Board mission briefing outlines the experiments that are going to the ISS. NASA actually likes to call these investigations instead of experiments. Technically, an experiment's goal is to prove or disprove a hypothesis, and an investigation is more about gathering data. Potato, potato. There are over 1,000 kilograms of investigations headed to the ISS this weekend. Access to space gives scientists and engineers the ability to test things that simply aren't possible on Earth. There's the height advantage, which means we can look at a lot of the Earth at once without the curvature of the Earth getting in the way. There's the obstruction advantage. We can see things in space without the Earth's atmosphere getting in the way. And there's the gravity advantage. We can sustain a microgravity environment for more than a dozen seconds. The presentations also showed me the breadth and diversity of investigations taking place in space. To give you a taste, here are my personal favorites that are part of this mission. Full disclosure, I'll probably be too casual with some of these terms, so feel free to correct me in the YouTube comments or at EEsTalkTech.com. First, there's a DNA-RNA sequencing kit designed to find unknown microbes on the International Space Station. It's called the Biomolecule Extraction and Sequencing Technology Investigation, or BEST for short, BEST. In my opinion, this is the best acronym of them all. They can find most of the bugs on the ISS with their current culture-based processes, but this kit allows them to find other microbes. It'll also let them track mutations of known microbes. Apparently, spaceflight causes genetic, epigenetic, and transcriptomic changes. There's also a sextant for navigation practice and some medical tools to monitor astronauts' eyesight. Apparently, long-term spaceflight messes with astronauts' eyes. There's a liquid separation tool that uses surface tensions and capillary forces to separate liquids. Here's Andrea Adamo, founder and CEO of Zyput Flow Technologies.
So if you see here, there's a device. You have a two-phase flow coming from the bottom left. You have water in red, and the clear liquid is toluene in this case, an organic solvent. So it gets into the device and gets continually separated.
Normally you'd have to let liquids settle, think oil and vinegar salad dressing, but this does it while liquids flow, and they want to try it in 0G. Speaking of salad dressing, there's also an enhanced vegetable grower on board. Astronauts will record the flavor and texture of the plants, and the results will be compared to a control sample in Houston. Apparently, even salad is an investigation in space. Another interesting part of the payload is an array of CubeSats, one of which has been dubbed Cubert.
Cubert stands for CubeSat Radiometer RFI Technology Validation Mission. Kind of a long name, a mouthful there.
This is Joel Johnson, the Electrical and Computer Engineering Chair at The Ohio State University.
Cubert is a radiometer, which means a sensor that tries to measure the amount of power coming in the electromagnetic spectrum coming from Earth. And in particular for Cubert, it's a microwave radiometer. So the part of the electromagnetic spectrum we're looking at is in the microwave region for us between 6 and 40 gigahertz.
Because of Earth noise and increased spectrum use, current radiometry measurements are becoming noisier and noisier and will possibly become unusable in the not-too-distant future. The goal of these CubeSats is to monitor these environmental factors and create a system that will remove noise in real time. When I sat down with the professors responsible for the program, they mentioned that the emissivity of water was a deciding factor in Earth noise, which was pretty fascinating to me. Sensitivity to water vapor peaks around 24 gigahertz, which is right in the middle of the allocated spectrum for these tools. Vegetation and soil moisture also play a role. There are also 2 other CubeSat arrays that are exploring cost-effective alternatives to expensive full-size satellites. I don't have time to go into full detail on these in this podcast, but they're pretty nifty. I sat down with these professors later on in the day, and there'll be another podcast dedicated to these projects. There's also a concrete project. Concrete formation is a pretty well-defined terrestrial science, but it's not that well-defined in a microgravity environment. Here's more from Alexandra Rodlinska from Penn State.
And a lot of time when I'm asked what's the research when I do, and I just say simply concrete, people give me a blank look and say they don't give PhD for concrete research. Well, yes, they do.
The findings of this project are the first stages of exploring construction options for the Moon and Mars.
And we will need shelters for the human mission. We will need to protect the equipment, and we need to find a way to produce these shelters and produce a safe environment for humans or instruments to be in there. And it turns out that concrete is going to be our material to go.
Astronauts will take these pre-made baggies, kind of like Lunchables but for space concrete, and mix together the concrete mix and water. Astronauts will then arrest the concrete drying process using alcohol and send the results back earthward. This will give Dr. Redlinska and her team a chance to explore the different stages of development in the concrete microstructures. Concrete also has a huge impact on our life here on Earth.
And when I teach materials classes, I always ask students, what's the most widely used material on Earth? And the answer is water. What's the second most widely used material on Earth? And that's concrete. For every person sitting in this room, there is 1 ton of concrete being produced and consumed every year. And every ton of concrete is responsible for emission of approximately 0.8 ton of carbon dioxide into the atmosphere.
So can you use Martian soil or moon soil for concrete in low-gravity environments? We'll see. Finally, the coldest man-made spot in the universe will soon be the ISS. Led by Jet Propulsion Laboratories, 5 different research teams will share time on this project, the Cold Atom Laboratory, which is designed to cool gas particles to, quote, like 1/10 of a billionth of a degree above absolute zero. Yeah, that's nanokelvins. Here's more on that from Eric Cornell from NIST.
And I'm going to start right off by saying why, because why would you ever want to get that cold? And the answer has to do with really looking, if you look at the future, if you look at the trajectory of technology, of economics, of the technology that drives the modern economy, it's easy to understand that the future is in the direction of the very, very small. Small transistors, small computers, small nanobots. And at these very small scales, the physics, the science, the underlying thing that matters is called quantum physics or quantum mechanics.
I should probably mention that Eric is a Nobel Prize-winning physicist.
If you want to be able to design the technology that's going to underpin the economy of tomorrow, you have to understand quantum mechanics not just at the level of that junior level class you took in college. You've got to really get it. You've got to grok it. You've got to feel it in your bones. You'd really like to be able basically to see this stuff. And it's true that quantum mechanics is the science of the very, very small, but due to sort of a twist of fate, it's also the science of the extraordinarily cold. Getting extraordinarily cold has the effect of magnifying quantum mechanics up to the effect where you can see it. So you can actually see what amounts to waves of quantum matter a millimeter or 2 millimeters across. These things are called Bose-Einstein condensates.
Wait, waves of matter? More on that in a moment.
This idea, this sort of relevance, this connection between the very, very cold and the science which underpins the very small, which underpins the future of our economy, is not a new idea. In fact, there are hundreds of groups around the world here on Earth, including mine, which are studying this thing called Bose-Einstein condensation.
Sitting there listening, I had no idea what a Bose-Einstein condensate was. I imagine you might be in the same boat, so I did a little digging. A Bose-Einstein condensate is a quantum state theorized by Bose and Einstein and realized in 1995 by the same Dr. Eric Cornell that we were just speaking of. Essentially, if you supercool a gas, like super duper cool it, the atoms start to increase in size and behave as waves. Eventually, the size of these wave particles becomes larger than the average distance between these wave particles, meaning the waves will begin to interact. At a certain point, all of the wave particles, known as bosons, settle in the same quantum state and form one big happy quantum wave known as a Bose-Einstein condensate. The problem with this is that they're really, really hard to create. One of the reasons for this is gravity, hence the Cold Atom Lab. The microgravity environment of the space station will allow Dr. Cornell and his associates to reach temperatures colder than that of Earth. All of that without needing time from the astronauts because it can be controlled remotely. Pretty cool. Sorry, couldn't resist. Clearly, there's a huge breadth of projects invested in this launch. After the briefing, it's back to the hotel to get some work done. It is a work day after all. And the day concludes with a dinner with some of the other attendees because what engineer doesn't love a meal with a bunch of complete strangers? In a public setting, I almost always feel like the biggest geek in the room. Sometimes that's fun, most of the time it's not, and I'm sure a lot of you can relate, but this was different. There's something about being in a room full of other self-proclaimed space geeks that really made me feel at home. After a little too much of the good luck ice cream that Orbital ATK special orders from a local shop, it's chocolate with chili powder and cinnamon, which is surprisingly okay, it's time to rest up for day 2. Day 2 starts at 8 a.m., which is not that bad until you factor in a couple-hour time change for me. I quickly wake up, though, as we all hop on a bus to go out and visit the rocket. All right, so we just drove up to the rocket on the buses. Naturally, we aren't able to go right up to it, but we're pretty darn close. Closer than you'd normally get to a fully primed rocket anyways. You can see there's just kind of this odd silence. Surreal is a term thrown around a lot by launch first-timers like me, and though it feels cliche, it's probably the best word to describe the feeling. It reminds me a bit of my childhood when I could catch a glimpse of the Matterhorn at Disneyland while driving up to Grandma's house on the 5. There's this academic knowledge of a whole group of people living in their little, complex, separate world, and the side of the monument is just the surface of it. After 15 minutes of staring, it's time to head over to what becomes my favorite stop on the tour, the Horizontal Integration Facility, also known as the HIF. Before we get to the HIF, I want to take a quick break and thank the folks here at Keysight for sending me out to this event. This type of thing is not something I'd normally get to do as part of my day job, so I'm going to essentially treat us as a sponsor for this podcast. By the way, if you like this podcast episode, make sure to share and subscribe, and maybe I'll get to do more things like this in the future. So, sponsor stuff. We have a pretty exceptional promo running for oscilloscopes right now. If you buy a new Infinivision 3000, 4000, or 6000 X series scope with the software app bundle between now and August 31st, you get your choice of a free high-end probe worth $2,000 to $4,000. There's an active single-ended probe, a differential probe. There's this dual input wide dynamic range probe that's pretty cool, or you can get a power rail probe. More details for that are in the show notes below. I absolutely love these scopes, so if you're looking for one, make sure to check one out. And thanks again to the Keysight powers that be that made this trip and this podcast happen. Let's get back to space stuff. We were just about to go see some more rockets. So this is the Horizontal Integration Facility. This is where they actually assemble the rockets before they go into space. So we're gonna go inside. We had to leave most of the camera stuff outside, and there's a bunch of stuff we can't show for like trade reasons and all that. At the HIF, we get up close and personal with OA-10, which is the next scheduled launch for Orbital ATK going in the fall. So we have a booster getting connected to the main body of the rocket. It goes all the way down there. Naturally, it's only partially assembled. The HIF is the place that takes all of the pieces and parts from around the world and connects them into one cohesive vehicle. First, the Cygnus spacecraft gets unpacked from the shipping container and placed on a separate ring. It then gets flipped to horizontal, and the Antares rocket gets placed on the transporter erector launcher. The Cygnus and its fairing, which is sort of like a protective covering, get loaded onto dollies and stacked on the Antares rocket. The entire thing then gets rolled out to Launchpad 0A about a mile away. Due to the presence of active ordnance, aka rocket fuel, and export control technology, aka stuff we don't want other countries seeing, all wireless devices had to be left outside, and our picture taking was pretty limited. So I can't show you the advanced piping and routing that is the backbone of the Antares rocket engine, but think copper shiny jet engine plumbing on steroids. There's a field fox right there. Again, it was fascinating to me to see so many teams working on so many discrete but integrated projects.
We have a rolling clean room that will be rolled over on one of those transporters, and it comes up to the nose of the rocket. We open up the... So it'll actually stay
a rolling clean room. That's pretty cool. Here's Mike Brainerd describing the rocket that's currently being integrated. The Cygnus module comes from Italy, and here are some of the other components.
Two Russian RD-181s. Like I said, they're shipped over here. We integrate those here. Orbital ATK built feed lines and thrust structure. All that shipped from our Chandler facility.
Okay.
And the feed line manufacturer integrated here, integrated to the first stage. Big fuel tank.
So this is fuel tank here?
Yeah. You can see the dome of the tank.
Yeah. Okay.
So you got that tank goes there.
Yeah.
The big one in the front.
Okay.
Yeah.
And then up top?
That's the second stage, Faster 30XL, solid rocket motor built in Utah by Orbital ATK.
To watch all of this come together in this sleepy backwoods town feels a little bit ironic. A quick pit stop for a press conference, and it's off to the Range Control Center. The Range Control Center, or RCC, acts as the sort of mission control for launches and other on-site missions. This is where I start to see the work of yet another set of behind-the-scenes teams. Meteorologists to check winds and weather, radar controls to monitor air and boat traffic, because the previous launch actually got scrubbed by a small boat that drifted too close, technical teams to handle copious amounts of real-time data and processing, specialists manning custom rocket system monitoring software, and more. The ability to photograph any of this was again limited, but it looked something like the systems you'd see bad guys working on in a James Bond damn hostage situation.
A lot of the stuff that Mars uses to run all the controls on the Launchpad are based off some commercially available control software. It's very much like running a refinery.
Okay. This is Frank Bellinger, the Wallops Flight Facility Technical Director, giving us an RCC rundown.
The area down here on the main floor is for the Antares launch, filled with Orbital Sciences employees looking at launch vehicle data, Cygnus, Orbital Sciences Cygnus employees looking at the spacecraft vehicle data, folks from the Virginia Commercial Spaceflight Authority who are busy looking at Launchpad data come in, and all working to a successful launch. Well, each of those groups has basically their own countdown going on with their own people that they're talking to through the associated intercoms.
Each of these teams come together and repeatedly rehearse each launch under varying circumstances and environments so that when the day comes, they're ready to handle any surprises. It's humbling to think that each of these workstations essentially represents a mission-critical team. We hop back on the buses and head over to the Space Balloon Research Center. Space balloons sound a little bit counterintuitive. After all, how can a balloon float if there's no atmosphere? Well, they go up to 120,000 feet, so not really into space, which space more or less starts around 100 kilometers. It's called near space. Here's a little more on the subject from Frank.
At that altitude, they're above 99% of the Earth's atmosphere, so it's about minus 80 degrees Fahrenheit up there. There's essentially no air. So it's a challenging environment, but it's a great environment for people who want to do space science. It lets them develop instruments that will make the next step into a full-up satellite. The advantage here is after they fly, we bring them down on a parachute, recover their instrument, and they get to fly again.
These balloons are described to me by Gabe Gard, who's the missions operations manager for the balloon program, as football field-sized, ultrasonically heat-welded trash bags. Really. They're huge 0.2 to 0.8 mil thick plastic bags that can stay in the sky for weeks or months. That's about the thickness of a sandwich bag, but the plastic is a little bit sturdier. Sometimes referred to as the beeline to space, balloons are the quickest and most cost-efficient route to near space. They can also be launched from nearly anywhere on the globe. Gabe, for example, has spent a collective year living in Antarctica for balloon missions. Why Antarctica?
In the Antarctic summer, which is our winter, a cyclone is set up over the South Pole where the upper air currents just swirl. So we can launch a balloon up into that, and it can stay airborne for a long time, just swirling around the South Pole, and then when the science is done, we can bring it back down and recover it.
Remember when we found the giant hole in the ozone layer over Antarctica? Space balloons were the vehicle for those measurement tools. The generally flat geometry of the universe was also confirmed by a balloon-borne investigation. These balloons have also recently been paired with a giant gimbal known as the Wallops Arc Second Pointer.
This thing can point at a dime about a mile away and not move off of the head of the dime. And so it can maintain that kind of accuracy from a balloon, which is pretty impressive because balloons just kind of bobbing up around there. So this was a development here out of Wallops, and our guys have worked on it for several years. But it's a really big boon to science that has come and basically built their telescopes onto the gimbal, the structure. And so this one is heading to Antarctica for this year, along with that truss structure. It's a collaboration between Wallops, NASA, and the science team out of Washington University. But they'll head down there, and they've got a 30-day or so flight lined up to explore the deepest regions of the Milky Way. So
we then float out of the Balloon Research Center and file into a giant machine shop, part of the Sounding Rocket Lab, where we meet this fine fellow.
My name's Joe Schaefer. I'm the Orbital ATK Program Manager for the Sounding Rocket Program. And joining me today is Harold Cherix. He's our Production Manager. Let's start with, do people know what a sounding rocket is?
No one really wants to admit that they don't, so the group is silent.
Alrighty. Okay, these are suborbital. They're up in space anywhere from 5 to 15 minutes before they re-enter.
Scientists from NASA, universities, or companies will get a contract to build the desired equipment. This facility builds a rocket and integrates that equipment. The rocket eventually gets launched, spends a few minutes in space, and then...
Some of our systems will go splash either on the land or in the ocean. Other of our systems will be recovered. We have both land recovery and water recovery. We've been doing this for about 50 years, so Elon Musk talks a lot about recovery and reuse. That's old. That's nothing new.
They're not at all a competitive bunch.
So what we're going to do today is talk to you about the vertical integration we do to help create a sounding rocket. So you're in a machine shop right now. We take raw material in, and then we process it to develop the different mechanical structures that help comprise the sounding rocket. Earl?
This machine shop, much like many others you've been in, but we build rocket parts. I would say 90% of what we build here is aluminum, 6061 T6. Most of that aluminum either comes from a round forging or flat sheet stock. We don't do additive manufacturing here yet. That's because Joe won't give me the budget. It's quite a large budget too, just let you know. I'm gonna plug in what I can. So we have lathe mills. We have 15 machines ran by 9 technicians.
The machine shop is littered with rocket parts stacked up like empty cans in a recycling bin. Here's a taste of some of the parts they build.
But let me take you over here and show you, we developed in-house. These tubes are internal to the rocket. So this mounts inside here, and either due to spring pressure or a small rocket motor, this will come out. And if you notice, this causes it to spin. So it's spin stabilized on the way out. So this either has an electronics package that it pushes out, or a small luminescent chemical so that we can measure the winds at upper atmosphere. So it'll create a small glow, and using ground-based camera systems, you can tell which direction and what speed that it's moving at.
What's that operator doing now?
This guy? He's probably drinking beer. This is a nose cone.
Good for him.
So what happens is that's a manacle ring or a V-band joint down at the bottom, and we fire a pyro, it cuts it and allows the springs to push this off to expose scientific instruments. What's on the outside coating here is a sprayed on RTV silicone. You can actually touch it. Just touch it lightly because this will fall. But what happens is on the way up, it gets really hot. This will ablate and take away some of the heat so it doesn't cause the nose cone to melt.
One of the benefits of sounding rockets is the possibility for extremely fast turnaround times. How fast?
Typical, the small end of the range is about 4 weeks if we've got a quick react. The other end, there's a payload that we've been trying to get launched for about 9 years now, and the scientist is still working on his instrument to make it flight ready.
9 years? That makes me feel better about the timing of some of my projects. And they don't just build rockets, they test them too.
In this room here, we do our deployment. So we can do boom deployments, nose cone deployments, and stuff like that. That's a Kevlar curtain that'll catch anything you throw at it. We had to put a ceiling on it recently because the ceiling in here is not tall enough.
I get the feeling there's a story there. There are also some electrical test rooms with racks full of equipment and wrong-colored oscilloscopes, at least in my opinion. I did a little probing into what electronics they're using, but didn't get much info beyond the fact that the sounding rockets use an RS-485 communications bus. I'll have to bug them a little more next time. After a couple more technical presentations, we have a little chat with astronaut Kay Heyer. She talks through a lot of the processes, activities, and emotions that astronauts go through. Her talk doesn't deviate much from what you'll find in a standard astronaut interview, but there was a moment that stood out.
And I think that humans we're not built to fly in space, but I think that we're built to adapt.
This seems like a pretty obvious statement, but being surrounded by the teams of people working on slivers of the rocket and surrounding projects really drives this point home. She also talked a little bit about navigating around space junk and debris.
We have to be concerned about what happens if there's a satellite up there that explodes and sends debris all over the place. Is that going to be a problem? The big things, the big buzz phrases you're going to hear for the next couple of years is space situational awareness, and you'll also hear about space traffic management, STM, so SSA, STM. And what that means is navigating around all this stuff.
Kay's final words do make us a little nervous though.
We're all keeping our fingers crossed for good weather and everything going well tomorrow, But these are operational things, so you know that there's always the potential the weather could get us, or some technical issue. And let me tell you, we're just not going to go if it's not safe. It's just not worth it. That's why we have set criteria for that.
After all, the launch already got pushed back a day because they needed to run more tests. So, with our official tour over for the day, we head out to get tacos, which are pretty good by East Coast standards, and worry about Kay's parting words. There's also some debate about whether or not it's worth pulling an all-nighter into day 3. Why pull an all-nighter? Well, day 3 starts at 1:30 in the morning. I'm not in the all-nighter camp. I had my share in college, so I head back to the hotel for a nap, wake up at 1:30, munch gas station donuts and coffee, and drive to meet our bus in the pouring rain. Not a good sign. I expect a pretty subdued bus crowd given both time and the weather, but the energy is palpable. You can feel the anticipation.
Oh, I can feel it.
Federal guards escort us and the media to the launch viewing area. As the crow flies, we're roughly 2 miles from the rocket, which is about as close as anyone gets to these things. I set up my camera gear alongside some other folks and glance down the line of media photographers, and there's easily over $1 million worth of camera gear here. Loudspeakers stream the mission control comms, and we start to get even more worried. The weather folks over at the Range Control Center don't like what they're seeing and move the launch target time to the very end of the 5-minute launch window. We hear words like anomaly and, quote, verifying the authenticity of the fire alarm, and get more nervous. I get more coffee and donuts from the catering tent and wait. Apparently, donuts are my nervous food. T-minus 12 minutes, and it's time for the go, no-go launch poll. Everyone around me goes quiet as they work through the launch poll checklist. Over the loudspeakers, we hear,
NLM is go for launch. Launch team is go to proceed with final countdown at L-4.
The group collectively releases a sigh of relief and some cheer. We're launching today. We buckle down for the 12-minute wait. "30 seconds left, and all we can do is fidget and wonder if our camera settings are correct. 10 seconds. The iconic countdown starts.
T-minus 10. Mark. 5, 4, 3, 2, 1.
That was audio from NASA, but it actually sounds pretty different from where we're standing. It takes a full 14 seconds for the sound to reach us, so it's interesting to hear the reactions from our perspective. Here's what we're hearing and seeing.
3, 2, 1.
Everything lights up. I'm struck by how slow it looks at first and how the 200-foot flame does a weird glitch dance. The sound hits us. Based on my audio recorder, it's roughly 30 to 50 dB louder than us talking and cheering. You can feel it in your chest. It's like fireworks, but louder and less bassy. The sound slowly fades to a low rumble as the rocket reappears above the clouds. A few minutes later, the light cuts out. Because Stage 2 uses solid fuel, there's no throttle. So the Orbital ATK telemetry team calculate the velocity and position of the craft. With this telemetry data, they know how long they have to wait before igniting the second stage. This ensures that they only need minimal adjustments to get in sync with the ISS in orbit. Adjustments require fuel, which means weight, which means cost. And private space, and really all of space, is all about cost per pound into orbit. That's why the launch window was only 5 minutes. It was a cost play. Cost was also the big factor in the decision to retire the space shuttle. Stage 2 kicks in and it becomes the brightest star in the sky. Slowly, though, it fades out and is gone. It's now past 5 a.m. and people start to pack up, tired but happy. The firefighting teams hop into their fire trucks and drive towards the launch pad, and I can only imagine the relief of the teams that have spent months and years on these systems. You never know, though, as their voices ring out over the loudspeakers, working through their post-launch checklists.
Copy all ops 2. We'll check 41 complete and site control.
They are a little more casual, though. A little bit of pride and relief sneaking past their professional masks.
Site control going back to step 489. Were you able to remove that?
There are also some anomalies, so it may still be a long day for a few folks.
Okay, copy that. FTS-A SNA and FTS-B SNA are both neither safe or arm and yellow as expected. FTS Ambi Loop shows open and green. That's not as expected.
After this 2.5-day space bonanza, I say goodbye to my new friends and start the long trip home to Colorado. While driving across the massive Chesapeake Bay Bridge and flying over the Rocky Mountains, I have some time to think about something Kay Heyer said in her talk.
And I think that we're not built to fly in space, but I think that we're built to adapt.
I can't help but resonate with this in the moment. I'm driving over a 4.3 mile long steel bridge, which when it was built was the largest overwater steel structure in the world. I'm flying over half of the USA, a trip that would take weeks without technology. I'm using my phone, which is communicating with satellites, which are also communicating back to the Earth as a map. Then I think back to the rocket launch. Months, years, and careers were spent making that launch happen. Even more months and years of time were dedicated to the cargo. Even more time has been dedicated to having a place to put it all, the ISS. Teams upon teams, collective lifetimes of effort, all boil down to a single, fiery, loud instant. I dwell on Kay's statement. We're not built to fly in space, but we're built to adapt. Clearly, that's why we have spacesuits. We also have 4-mile-long bridges, airplanes, and sleepy towns that transform into technology centers. So I agree. We're not built to fly in space, but maybe we were made for it. I'd like to thank NASA, Orbital ATK, and the wonderful Laurie Bonneau, John Mitchell, and John Huntington for letting me use their amazing pictures. Laurie and John M. both have killer Flickr pages you should absolutely go check out, especially if you want to see more pictures from this trip. And John H. has some pictures over at controlgeek.net. Links for those are in the show notes. Go check them out. I should also mention that while I've been recording this, Orbital ATK was purchased by Northrop Grumman and is now known as Northrop Grumman Innovation Systems. And if you would, please do me a personal favor and give the EEs Talk Tech podcast a review in iTunes or whatever podcast system you're using. I would really, really appreciate it. You can also find more from us on the Keysight podcasts and Keysight Labs YouTube channels or on Twitter. Thanks for listening and watching. It's been a genuine pleasure.